Yes, welcome back, everyone. If you saw an ad before the YouTube video, it's not because of me, it's because that lovely introduction got copyright striked. Probably didn't happen just because this video is unlisted, but just in case, that's what the ad was for. Congratulations on paying NBC by watching this. Today, we are talking about the area under a curve. If I can spell. Area under a curve. And we really have a couple of ways of thinking about this. For today, we're going to handle approximate area. Of most curves. So by that, I mean, we're not going to be able to find the exact area in the sense that, you would ask yourself, if I were painting this or coloring within the lines or something, can I find the amount of paint I would need or the amount of marker I would need? We're instead going to be getting a close approximation. So that's what we're going to handle today, and pretty soon we'll see how to get the true area. So let's just talk about some curves, finding the area of an example curve. So let's look at the area under a line. And this shouldn't be too bad for you guys. I'm going to zoom into the first quadrant here, and let's just grab 2 points. Connect them with a line. And if this is y equals 2, this would be x equals 4, y equals 3. So this is the point 0, 2. This is the point 4, 3. And a little bit of y equals mx plus b action tells us that this is 1/4 x plus 2. So let's maybe just talk about the area here. I'm going to draw this in. I'm going to use my fancy-dancy highlighter to talk about the actual area here. It's nice that we're working on an iPad now, because this gives me a little bit more ability to do some fancy things. This is from 1 to 3. So in some sense, we would ask ourselves the question, what is the area under, and by that I mean between the curve and the x-axis, under f of x from x equals 1 to x equals 3. This is really, in some sense, the sorts of problems we want to be able to solve. And let's take 10 seconds. I realize I don't want to waste your time. 10 seconds to just think about this and see if you can give me the exact area. I know I said earlier we would say approximate area, but on this one we can get an exact area today. So today we can get exact area for lines. So does anyone, hopefully you might have come up with the solution as to how to do this. Because this is a rectangle, really it's a square, plus a triangle. And we know how to calculate areas for both. Right, so if I look up at my image here, my graph, and if I demarcate it along this line here, not only do we have a triangle, but we actually have a right triangle. So we have a rectangle of height 2, width 2. So let's draw that here. And then we have ourselves a triangle of width 2. And we don't quite know the height of this triangle, but we can find it out just by looking at the points here. So the point on the corner, I can find that out from the function. This is the point 1, and then it's 2 plus a quarter, and I'm going to call that 9/4. And then this other point is 3 comma 2 plus 3/4, which I'm going to call 11/4. So then the height actually of our little triangle happens to be 2/4, also known as 1/2. So that's what I'm going to do here. We're just going to add the two areas. So area of rectangle is just length times width, L times W, which in our case is 2 times 2. So we get 4. And I'm just going to leave it as 4. Really, this is like just units squared. Or square units, you might have heard. And then the area of a triangle, and a lot of you might not have remembered what the area of a triangle looks like, or what the equation is. It's 1/2 base times height. So the base here is 2 and the height is 1/2. So we end up with 1/2. And this is also square units. But that means that the total area, hence total area, is going to be 4 plus 1/2. You can leave it like that if you want. I'm going to call this once again 9/2. So that's how we could do it for a line. Area under line. But at the end of the day, all these functions we've seen are definitely not lines. So we see a lot of functions that are not lines. So we approximate those. So we approximate their areas. And how do we do this? And when I say we, I mean lazy mathematicians. So how do the lazy mathematicians approximate the area under curve? And this is just with rectangles, with a whole lot of rectangles. The reason being because length times width is really easy to calculate. And other shapes are harder. Call this other shapes. Other shapes are harder. That's what I meant by the lazy mathematician. The lazy mathematician just wants to work with rectangles, and so that's what we do. So let's see how we do this. Let's just do an arbitrary curve. So my arbitrary curve is going to look something like this. And let's say I want, I'm just going to call this spot x2 and this spot x1. And I want to approximate, put little dots there, want to approximate that area. So once again, I'll shade this in so we know what we're talking about. So I want to approximate this. Let's call it curve f of x still. I want to approximate this with rectangles. And so I need to know how to find the height of each rectangle. Really, first I'm going to ask myself how to choose the rectangles. This is step 1. And step 2 is how do I know the height and width. So let's just say between x1 and x2, let's say I'm going to divide it into 4 rectangles. Let's do 4 rectangles for now. And let's do equally spaced rectangles too. You know, you want them all to have the same width. So to do that, I'm just going to, kind of guesstimate in half, half, and half. And then I'm going to draw these straight up. And you guys are all yelling at me like, those are not rectangles. Those are some weird blob-shaped things. Yeah. And so this is the tough part, is how do I know the height and the width? Well, we can find the width. It's not too bad. If they're equally spaced, the width, well, what's the distance between, it's the total width. The total width is x2 minus x1. So then the width of a single rectangle is x2 minus x1 divided by 4. Because I have four total rectangles. That's all that's going on there. The height's trickier. The height is kind of up to us. Up to us to decide. And the mathematicians have given us three sorts of easy places to calculate, so to speak. They do what's called left endpoint. They do midpoint. And they do right endpoint. So a left endpoint would look like, and I'll draw these maybe all in different colors. So what the left endpoints is going to look like is I'm going to use the left 4 points. Do this in blue. And I'm going to make rectangles out of those. Now what that means is that I'm going to draw a horizontal line until I run into the next rectangle. And you can start to see now where my rectangles are here. I have 4 rectangles. If I want to work with the midpoint, that means I'm going on the curve. Now this is the height of the curve at the midpoint. This is not the height of the rectangles I've already drawn. The height of the curve at the midpoint is going to be like here, 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 and here. And now I'm going to make rectangles with those as the height. And so to continue with rectangles as those as the height, my rectangles actually extend past the curve in a lot of places. And finally, if I'm working with the right endpoint, that means I'm asking myself where would the rectangle run into the curve on the right corner of the rectangle. And now you can start to see some funny stuff happen. That's actually that the left and right endpoints agree at some places, but the rectangle they're talking about is a different rectangle in each case. So the endpoints line up, but in a lot of cases, right? So the blue and the red dots overlap. However, the rectangles that they trace out do not overlap. So that's really the big difference here. And we're going to want to ask ourselves, what are these heights actually equal to? And it's not too difficult. The height of each rectangle is equal to f, and then you evaluate at the point, the colored point. So f evaluated at the colored point is the height of the rectangle, because f is just, the height of the curve. Okay, so this is the overarching picture that you want to be keeping in the back of your head the whole time, but this isn't actually what the way that we're going to calculate these things. And I'll, maybe you guys are going to be like, why did you show me this stupid picture then? Well, this is what you want to keep in the back of your head the whole time. Obviously, we're going to be working with numbers instead, and so you might want to see this in terms of numbers. So we said that the height was f evaluated at the points. So here's our width, w. There's our height, f evaluated at the points. So what is the actual formula we use? And now this is the thing that you guys are going to want to rely on for doing your homework problems. Is, a problem is going to say, this word 4 that I used, let's do 4 rectangles of the same width. The problems are going to say something along the lines of n subintervals. So the problem's going to say something like, find the area of f of x from x equals x1 to x equals x2, and it's going to say using n subintervals and the left and mid or right and point. So n subintervals is, the n is playing the role of the 4 that we saw up here. N subintervals, this was like 4 subintervals. it's going to say x1 to x2. Those might be numbers 1 to 8 or negative 2 to 4 or something like that. F of x is going to be some function x cubed or 2x or something. And then it's going to tell us the left endpoint, the midpoint, or the right endpoint. And when it says that, then we're just going to follow what I produce for you. So all we're thinking about is calculating 4 rectangles here. The area of 4 rectangles, or n rectangles in our case, n rectangles, and then we need to know their width and their height. So the width of our n rectangles is the same as before. It's x2 minus x1 divided by n. The height of each is f of some point. So the area of each rectangle is the length times the width, or the height times the width, we can say. H times W, but what is that? It's F, some point, times x2 minus x1 divided by n. So that's the height times the width. But to find the total area, my total area here, I would end up adding 4 rectangles together. So I'm going to add total area will be all rectangles added together. So that means you would see some sort, we'll see a lot of plus signs. Let's look at the actual formulas now. So I say the actual formula we use, and then we talk about a bunch of this stuff. Okay, here are actually the formulas. This is the left endpoint. This is going to be x2 minus x1 divided by n. You'll remember that is the width, and then the height of each rectangle, we can actually add all the heights together because this is like factoring out the width from every piece. So we're going to add the heights together, and if we're starting on the left, if we start at the left side, that means we actually start at f evaluated at x1. Because x1 is the farthest left point of our basically the area that we're looking for. It's the farthest left point in terms of the height of the area we're looking for. And then if I run back up here really quick, I see that the width of each rectangle is actually, since the width of each rectangle is x2 minus x1 divided by n, then I just have to shift the x inside of my function here by that much to see the next point that we evaluate at. So I've just decided to shift my function, what I'm plugging into the function, by 1 rectangle's width. And then you add again. I'm going to shift by another. This is x2 minus x1. Shift by another one of the widths. And I'm going to keep doing this until I end up at x2 minus one of the widths. Now that might not seem immediately clear as to why you keep doing that until you end up at f of x2 minus one of those widths. But the reason is that if I look at where x2 is here, if I look at where x2 is there, and then look at the spot that my left endpoint we'll remember is blue. So my last left endpoint right there is the blue dot. And the blue dot is exactly, oh, I do not know what I just did. The left endpoint, the blue dot is exactly one width away from x2. So you step to the right until you end up really at x2 minus one of those widths. And that's not remarkably clear what that's going to be. Another way you can think about this is its equivalent is we're going to have the same thing out front, x2 minus x1 divided by n. But then we end up with, oh boy, this is the same, f of x1 plus f of x1 plus x2 minus x1 divided by n. We're going to keep stepping forward, but where do we end up? Another way of writing the spot that we end up at, it's actually x1. Make sure that looks like a 1 for you guys. F of x1 plus, this is n minus 1 x2 minus x1 divided by n. It's the same thing. So if you want to calculate that out, basically I'm saying we step to the right n minus 1 times. So just as on the top in this graph when n was 4, and we started here and then we stepped to the right, we started here and then we stepped to the right 1, 2, 3 times. When n was 4, you step to the right 3 times. When n is n, you step to the right n minus 1 times. So a couple ways of thinking about it. I'll call this LE for left endpoint. And then there's a version where you can do the midpoint, and this is a bit trickier to write out. So the midpoint version, MP for midpoint. Our width of each rectangle is the same. Still x2 minus x1 divided by n. But now we are starting at x1, but we're adding one half width to it. If I scroll back up here, if I look at the first yellow dot, I've started at x1. x1 starts here, and I've moved by 1/2 of my width. So I've started there, and I've moved by 1/2 of my width. So that's what's going on in the formula, is we've shifted ourselves by 1/2 in width. And then everything else looks the same, and that's kind of nice that everything else looks the same. Make sure that you can read that. This is x1 plus, of course now this is just 2 times, this is actually, it's going to step up by, you start out with 1/2, you go to 3/2. Because that's really me adding 1 onto 1/2. I'll rephrase this in terms of 1/2 so it looks a little prettier for you guys. You'll be able to see it a little bit better then. 1/2. And then we keep going until we end up at n minus 1. This is not n minus 1/2, it's actually n minus 1 plus 1. It's 2n minus 1 plus 1 halves, or equivalently n minus 1 plus 1. I'll rewrite that for you. This is n minus 1 plus 1 half x2 minus x1 divided by n. And that looks terrible, but it'll make more sense when we do it as an example. So I'm going to leave it like that for now. It'll definitely make more sense when we do it as an example. Just as the above, you can think about it also as an x2 minus a 1/2 times the width. Whichever way works better for you, that's the way you want to think about it. Oh, I guess I could. Yeah, this is probably the best way of writing it. You end up at n minus 1/2. That's the best way of writing it. You end up at n minus 1/2 there. And as I said before, this will make a lot more sense when we do it as an example. And finally, for the right endpoint, I'm going to separate this piece off so you just have them in three nice rows. The right endpoint is still going to be the same width, but instead of starting at x1 like we do on the left endpoint, we just shift every piece by 1. So we actually start at x1 plus x2 minus x1 over n. And so on. And in this case, since it's the right endpoint, we should actually end up at x2. Because if I scroll all the way up to the top, you'll notice that my right endpoint, my piece in red, ended up, where is that? That's right at x2. So as always, we'll see this with some examples, and it's going to help us out quite a bit. So let's do one of these. So this is going to be, it's going to say let f equal x squared, and consider the region R under f from x equals 0 to x equals 1. And sometimes they'll say this, the interval 0 to 1. You'll see either version. There's our interval notation coming back. So we consider the region. I'll just draw this out really quick. Very tiny. That's what our function looks like. It's half of a parabola. There's the full parabola. But we're considering it from 0 to 1. This is x equals 0, x equals 1. And so we are talking about this area here. And if I could color in the lines, then that would actually be the right area. So the problem then says divide the interval into 4 equal subintervals. This is where you guys should all be thinking about n equals 4. So n equals 4 equal subintervals. And then it says it says approximate the area using the midpoint rule. And approximate the area using the midpoint rule. So we're going to divide the interval into 4 equal subintervals, and then the midpoint rule tells us, so that told us n, and the midpoint rule tells us we're using our middle formula here. And I know it looks crazy right now, but it's going to make sense. So let's just see if we can do this. So let's use our formula. Use the formula above. We should first identify x1 and x2. We can identify x1 and x2 really easily because it tells us from x equals 0 to x equals 1, or the interval 0 to 1. It says x1 is 0, x2 is 1, which gives our formula MP equals x2 minus x1 is just 1 now, because 1 minus 0 is definitely just 1. So x2 minus x1 is 1. N is 4. So I'm using this, and I'm using those in the formula. 1 minus 0 over 4. And then I have f. We'll do this in 2 steps. F of x1, which is 0, plus x2 over x1. It's 1 minus 0 over 4 again. But there was actually a 1/2 out front. So this is 1/2 times 1/4. And then I look back up and I see the next term is 3/2 times that. Three halves times 1/4. And I'm just going to keep stepping up. 0 plus 5/2 times 1/4. And actually, I know when I can stop here. 7/2 times 1/4. I know when I can stop because stop when I have n terms. So when we made n equal to 4, and there happened to be 4 terms here, 4 f's, so to speak, that's when I can stop. Now we'll find out what is 7/2 times 1/4. That's 7/8, and I was saying earlier that means that I would be 1/2 of 1/8, which is 1/8. 7/8 is 1/8 away from 1, which is what x2 is, and that's another way that I can know that I've stopped. But the better way to stop is you stop when you have n terms in your sum. So I'm going to rewrite this out. This is 1/4. Now I'm going to substitute, well, let's just rewrite this out. This is 1/8, f of 1/8 plus f of 3/8 plus f of 5/8 plus f of 7/8. But what is f? We decided that f, right at the top, it told us what f was. F is x squared. So when f is x squared, this is really 1/4 times 1/8 squared plus 3/8 squared plus 5/8 squared plus 7/8 squared. And I'm not going to waste your time calculating this out for you. The answer is 21 over 64. That's what you get as an approximate area. So the approximate area is an approximation to that piece shaded in green. And if I show you what that looks like up close more, right, this approximate area, our function looked like this. Let's call this 1 and this one 0. If I divide that into 4 pieces and use the midpoint, we're doing something like this. So these are actually the areas we've calculated. Switch to these areas are what we've actually calculated. And you can tell, you know, we've overestimated in some pieces, underestimated some other pieces, but that's not bad. That's a pretty good approximation. And so it starts to be a little bit crazy right away. You get used to it. And it turns out that we can use this to create something that makes our life easier. But I'll do one more problem, and then I'll send you on your way. So let's do this one more time. I'll do a problem with both the right endpoint and the left endpoint, so that you guys can at least see what both of those look like as well. So here we say let f of x (1 over x plus 1) and find the what does it say? It says find the approximate area of approximate area under f from 1 to 3 using n equals 5 endpoint and n equals 5 points, n equals 5 subintervals, and the right endpoint rule. So we want to translate this into something that we can interpret to use our formulas for. So there's our formula still. Right endpoint is the bottom one right there. I'm looking at it and I really need to identify x2, x1, and n, and also f to a certain extent. So let's just write that all down. F is already given to us. Give that a nice circle. N equals 5 is already given to us, so we just need to identify x2 equals 1 and x2 equals 3, actually. Of course, x2 is always the bigger number. x2 equals 3 and x1 equals 1, which means that, and this, you always kind of want to calculate this piece, this x2 minus x1 over n right away. What is 3 minus 1 over 5? That is 2/5. So this, just keep in mind, this quantity here is 2/5. So every time that quantity, this x2 minus x1 over n quantity shows up, just think about it as 2/5. That's going to save ourselves a lot of time. So this x2 minus x1 over n quantity in my right endpoint rule here, I'm looking at the right endpoint rule. It's going to be x2 minus x1 divided by n. So this is RE equals the 2/5 that I just calculated. And then it's f. Where do we start with the right endpoint? We start at x1 plus that ratio, that x2 minus x1 over n ratio. So we start at x1, which is 1 here, plus the ratio, 2/5. And then we work our way down, 1 plus, now I have 2 copies of 2/5. And then it's f of 1 plus 3 copies of 2/5, f of 1 plus 4 copies of 2/5, and finally f of 1 plus 5 copies of 2/5. And you'll recognize that last case of 5 copies plus 2/5, that's just f of 1 plus 2, which is 3. So this is really f of x2 in disguise. That'll tell you when you have to stop your adding numbers onto the end, as well as you'll eventually run into f of x2. So that's f of x2 in disguise. Then we can rewrite this out as 2/5. Call this 1 plus 2/5. Every time I see the 1, I'm thinking about that as 5/5. So 5/5 plus 2/5 is 7/5 plus f of 9/5. You'll notice I'm just adding 2/5 each time. 11/5. 13/5. 15/5. And what is 15/5? Well, that's just 3. And once again, that's f of x, 2. Now, finally, I like to translate this in terms of what f actually looks like. And we see in our case, f looks like 1 over x plus 1. Now, I'm just going to keep in mind that something like, keep in mind that 1 divided by 7/5 is 5/7, and so on. 1 divided by 9/5 is 5/9, and so on. So I'm going to call this 2/5. And then here I have 1 divided by 7/5 is 5/7 plus 1. This was just directly, that is what f of 7/5 is equal to. And then I continue to do that for each piece. 9/5 gets flipped around, my bad. 9/5, we're going to get 5/9 plus 1. We're going to get 5/11 plus 1. We're going to get 5/13 plus 1. And we're going to get really 1/3 plus 1 is this last piece. 1/3 plus 1. And the one last step, I'm going to combine all those terms on the inside. So they don't look great because it's a 7th plus a 9th plus an 11th plus a 13th and so on. So I'm just going to group my 1s together. And I get, this is really 5 times 1/7 plus 1/9 plus 1/11 plus 1/13. And you'll remember that actually 1/3 is the same as 5/15. So this is 1/15 plus 5. You guys might not believe me. Honestly, this is where you stop on exams because no simplifying. I just like to simplify for fun because I'm that nerdy boy. So what happens here, I have I'm dividing by 5 out front, and I have 2 pieces with a 5 on the inside. So really this turns into 2 times 1/7 plus 1/9 plus 1/11 plus 1/13 plus 1/15 plus 1. This is like kind of maybe the most simplified way you want to write it. You can convert to decimal if you want. So that's how you would do one with the right endpoint rule, and I'm going to do a quick one with the left endpoint rule for you guys so you can have at least seen all of it. One more time, let's do, so let's try f of x equals 4 minus x squared from -1 to 2 using n equals 3 subintervals. If I can spell right. N equals 3 subintervals and the left endpoint. So let's identify, as always, this is x1 and this is x2. My 1 looks a little bit like a 2, so I'm going to switch that around. x1 and x2. So then this lovely x2 minus x1 divided by n looks like 2 minus -1 divided by 3. Looks like 3 divided by 3 equals 1. Perfect. So that makes our life really easy, actually. The fact that this ratio is 1 means we can sleep easy. So if I use my left endpoint formula all the way up, right here, left endpoint, x2 minus x1 over n, that was just a 1 out front, and then I start at f of x1, and I just start adding this ratio to it. So that was my x2 minus x1 divided by n, and then I have f of x1, which is -1. Oh, God, I cannot draw. -1 plus f of -1 plus 1, because this is again our ratio. This is x2 minus x1 over n, plus f of -1 plus 2, because that's really 2 times x2 minus x1 over n. And you'll know that I'm done when I get to 3 terms, since n equals 3. So I know I'm done then, and this gets really easy. This is just f of -1 plus f of 0 plus f of 1. And I can calculate that out with f, because f is 4 minus x squared. This is 4 minus -1 squared plus 4 minus 0 squared plus 4 minus 1 squared. So what do I end up with? Well, I have 3 4s, that's 12, and I have -1 minus 1, that's -2. So I end up with 10. So 10 is an approximate area of this graph from -1 to -2. And if any of you, if I draw this out, I think you guys could believe me, because what does this look like? This is the point y equals 4 up here, and the graph looks something like that. It intersects at x equals 2, and so we're approximating the area here. So we're doing an approximate area of this. And yeah, this is, when you think about how many squares you could fit in here, you know, hopefully you can agree with me that you can fit, maybe didn't do that perfectly, but you can fit about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You know, we're not perfect, but you get what I'm saying. It's about 10 squares. You fit about 10 squares inside. So that's, you know, that's a quick and dirty version of seeing why this maybe should make a little bit of sense. Anyway, I don't want to spend too much time on it today. Use that Ask Your Instructor button if you run into problems. But really, you're going to want to think about these 3 formulas. And if it's making sense while you're doing what we're doing, then that's great. And if not, email me and do whatever else you have to figure it out. This is tricky, and there won't be that many test questions on it, so don't worry too much if you can't get it perfectly. But otherwise, just email me, hit the ask your instructor questions, and I hope you're all surviving the COVID just fine. I'm doing all right, going on walks and whatnot. I hope you're all staying healthy too. All right, I guess I'll see you tomorrow. Bye.